Thank you again for giving me the opportunity to present this work. And this work has been done in collaboration with Jesslyn Kaur and Professor Arun Kumar Pati, who are both at Harrison Research Institute at the time of this work. And I'm based in Seoul in Korea Institute of Science and Technology. So this work is called Remote Creation of Quantum Coherence via Indefinite Causal Order. And it has been published in Quantum Information Processing this year. So I go to the plan of the talk. First, I'll start with the motivation. Then I'll go to the background section, which involves quantum coherence and indefinite causal order, but I'll not talk indefinite causal order from a perspective of fundamental importance, but from a perspective of performing different tasks, that is the quantum switch. And then I'll go to the main results of the paper, which involves the introduction of the protocol of random preparation of quantum coherence, remote preparation of quantum coherence, and then after introduction of that protocol, I will assess the quality of our protocol with respect to different examples by evaluating the fidelity of the protocol in those scenarios. And I will end with conclusions and future directions. And of course, there are acknowledgements. Okay, so just 1 second. Okay. Motivation. So recently, the principle of superposition has been extended to the case of physical processes, and this has been very useful. So earlier, it was mostly for example, the phenomenon of quantum entanglement, which was at first stated for quantum states. The principle of superposition is vital there. But however, now recently, or even not so recently though, but it has been extended to the case of physical processes and, for example, these quantum operations. And it has been shown to be useful in aiding quantum communication and metrological tasks. The indefinite causal order that we are talking about here is, which we also call the quantum switch formalism, is nothing but the superposition of causal order of quantum operations aided by a control qubit. And this is one type of the application of superposition in quantum mechanics. So what are the practical applications? The quantum switch can give rise to quantum advantages in quantum computing, reducing the communication complexity, quantum communication, quantum teleportation, as metrological resource for quantum thermometry, and in the task of channel discrimination. And not only it's a theoretical possibility, all those protocols, but these protocols have been tested experimentally and proved in many different scenarios in recent years. And therefore, motivated by the above tasks that use this entanglement and quantum superposition of channels as resources, we ask the question whether we can create quantum coherence at a distant location using an entangled state, local operation and classical communication, and which is aided by the indefinite causal order. So next, the background section. First of all, this quantum coherence that we are trying to create is a basis-dependent quantity. And therefore, we have to fix the basis at first, which we call the reference basis. All the states that are diagonal in this basis are incoherent states or have zero coherence in the chosen basis. There's all the states which have non-zero off-diagonal elements in the reference basis form the coherent states, and these states will have a finite value of coherence. The quantification in terms of the off-diagonal elements in a quantum state in the reference basis gives us a measure of quantum coherence. So there have been many proposals for the quantification of quantum coherence, but we will use here one definition, which uses the L1 norm to quantify quantum coherence. So suppose we have a pure state, which is given by this summation I, CI, then there is the definition of this quantum coherence using the L1 norm is given by this quantity, a summation of over product of the absolute values of Ci and Cj, where I not equal to j. So it involves all the so it involves all the off-diagonal terms. You can see clearly from here. So this is for pure states. And now there are many important properties of quantum coherence. It's always non-negative, and it's only zero if and only if it's an incoherent state. It is monotonic under any incoherent operations, which is this relation is just a mathematical relation, and it is strongly monotonic. It does not increase on an average under selective incoherent operations, and it is a convex function of the state, and therefore we have this convexity inequality being satisfied by this L1 norm quantum coherence, and the L1 norm measure of quantum coherence satisfy all the above properties. Yeah, so let's just go to the next. Actually, I cannot see. Yeah, so now we will go to the next background required for our work, which is the indefinite causal order in the form of quantum switch. So in the classical world, we are predisposed to think of events occurring in a fixed causal order. However, it has been shown in quantum mechanics that one can have non-classical causal structures in which the order of events is not definite. It has been shown that such an indefinite causal order provides an advantage in certain quantum information processing tasks, quantum computation, and even in quantum communication complexity. In practice, one can implement an operation with indefinite causal order via the switch formalism. And in this formalism, there is superposition of causal orders of two or more quantum operations or quantum channels aided by a control qubit. So if we have two operations, M1 and M2, then a state can be operated either by M1, M2 or M2, M1 in the causal setting. That is to say, it can go through M1, M2 when the control state is 0, 0, or it can go through M2, M1 when the control qubit is 1, 1. Okay. But with the help of a control qubit, which is a superposition of 0 and 1, the input state can go through both the configurations at the same time, leading to superposition of causal orders. So now let us define the cross operators of M1 by X1, the set of these operators X1, and those of M2 by the set Y, which contains the elements Yi. Then the cross operator for the superposition of quantum channels is given by this quantity Wij. So what is the action of the switch and what is the output that is given out when a quantum switch, but when we say that the quantum switch is in action. So when the quantum switch acts on the input state, we get an output state, rho out, which can be written in terms of these Krauss operators, Wij, okay? And this rho C is the control qubit or the control state, whatever you want to say. So here it's just a qubit. We only work with qubits here. Excuse me. Now, the above formula represents the action of quantum switch that implements the superposition of causal order of two quantum channels via the control qubit. Now, excuse me, we go to the introduction of the protocol for remote preparation of quantum coherence. At first, without the indefinite causal order, but with the but protocol we introduce without the indefinite causal order, but later we will show the advantage when we use indefinite causal order for the same protocol. Okay, so here we introduce the basic idea behind the remote creation of quantum coherence. And let Alice and Bob share an entangled state rho 1, 2. Imagine that Alice has a state in her mind. I mean, she has complete knowledge about the quantum state. Now, Alice will perform a local unitary operation depending on the knowledge she has about the qubit. Then the shared state rho 1, 2 will undergo a transformation, okay, because of the unitary operation performed by Alice on her part. And then Alice performs a projective measurement in the computational basis. And as a result of this local measurement, we get a transformation of the quantum state shared by Alice and Bob, and conditioned on this measurements by Alice, which we can write as pi 0, which is 0, 0, or pi 1, which is 1, 1. And depending on the measurement outcome, she will communicate the classical information to Bob. After receiving the classical communication, Bob may or may not apply a local unitary operation depending on the protocol. At the end, the state of the qubit at Bob's location will have the desired amount of coherence that Alice wanted to create. So at Bob's location, we have the coherence after performing of all these measurements and unitary operations, which are expressed mathematically as equations here. And now, example, this is the main example, but we didn't apply indefinite causal order in the main protocol. But with the examples, we will show that if we apply indefinite causal order in the protocol, there is an advantage in this quantum information task of remote creation of quantum coherence. So we start with two completely depolarizing channels. We do the example with a maximally entangled state between Alice and Bob, and the noise comprising of two causally activated depolarizing channel acts on half of the pair possessed by Bob. Okay. So the state shared between Alice and Bob after the action of the overall quantum channel resulting from the quantum switch of two completely depolarizing channel is, I didn't give the exact form though, but I don't think it's needed. So let's go to the next step, which is if the measurement performed on the control qubit in the plus minus basis if the measurement is, so there is a typo. So if the measurement is performed on the control qubit in the plus minus basis, then the conditional state shared between Alice and Bob is given by rho 1, 2 plus. That is what we denote. And then after this, we may ask whether the superposition of quantum channels can preserve some entanglement for the state rho 1, 2 plus. To answer this question, we check if the shared state between Alice and Bob is still entangled by means of a PPT criterion, what we call the PPT criteria. And it can be stated using the PPT criteria of entanglement, that the state which was initially maximally entangled has become separable under the noisy scenario. Since now the conditional has no entanglement, we consider if there can be some other quantum correlation between Alice and Bob. For this purpose, we check the quantum discord in the state rho 1, 2 plus, and we see that this rho 1, 2 plus has a very small amount of quantum discord. Now, interestingly, we find that the quantum discord reaches its maximum values when the control qubit is in a maximally coherent state. That is an equal superposition of the computational basis states. This indicates that a maximally coherent control qubit enables to maintain a tiny amount of quantum discord that is shared between Alice and Bob. Following the stated protocol, we calculate the coherence of the conditional state at Bob's location, and we find there is a non-zero amount of quantum coherence if we apply this indefinite causal order. And counterintuitively, what we find that complete decoherence of the state did not take place, as in the case of completely depolarizing channel alone without the indefinite causal order. And an advantage can be gained with respect to coherence as a result of superposition of a noisy channel with another copy of itself. Even though there is no entanglement shared between Alice and Bob, there is a non-zero quantum discord present across rho 1, 2 plus. The non-zero discord helps to create non-zero quantum coherence with the help of indefinite causal order. So next we go to the example 2, which is an unitary operator and a completely depolarizing channel. So it's almost the same. However, in place of two depolarizing channel, one is replaced by a unitary operator and the another is a completely depolarizing channel. And almost the similar things happen, that with using PPT criteria, we inferred that the state shared between Alice and Bob is not entanglement. And the quantum discord is non-zero.
Just to interrupt, you have about a minute left.
A minute?
Yeah.
Okay. And let's just go to the results directly. The protocol just follows exactly the same as I have stated in the general protocol in the first few slides. And we see that similarly, we have some non-zero quantum coherence via the use of indefinite causal order. And we also consider two partially depolarizing channel, and we follow the same protocol. And I just show you the plot that we've calculated the quantum coherence, and we plot the advantage we gain in this quantum coherence protocol by calculation of the fraction of the difference in the fraction of the quantum coherence from the initial state without the indefinite causal order and with the definite causal with the use of indefinite causal order. And we see that we have always this quantity is positive, which shows that this indefinite causal order gives us an advantage in the creation of this coherence at a remote place. And so these are two partially depolarizing channels. And now we go to conclusions and future directions. So if Alice and Bob share a maximally entangled state, then Alice can create quantum coherence of any arbitrary qubit state at Bob's location perfectly by communicating one classical bit. This is in sharp contrast to remote state preparation, where Alice can prepare the qubit chosen from only special ensembles, that is, qubit chosen from equatorial or polar grid circles. If the shared state undergoes a noisy channel, then typically it loses quantum entanglement and other quantum correlations. However, if two noisy channels are in the superposition of indefinite causal order, then even though the entanglement is lost, we find that the presence of tiny amount of quantum discord can help to create a non-zero quantum coherence. And therefore, we have introduced a method for creation of quantum coherence at a remote location via the use of maximally entangled state. And this also, our work also shows that the creation of quantum coherence at a remote location can be enhanced by the usage of indefinite causal order or the quantum switch formalism. And the mechanism investigated here may provide better understanding on how to maintain coherence under extreme noisy channels. And in future, we will explore the possibility of preserving quantum coherence in the hot environments with the help of indefinite causal order. So these are some of our acknowledgements, and I thank you for listening to my talk. Thanks.
Thank you.